Hey guys, welcome back to day 30. We're talking about cells, battery, and fuel cells today. So batteries. We'll start off with a battery. And a battery, we know that E standard for a battery is positive, right? They're going to be voltaic cells. They're portable, self-contained power units that consist of one or more voltaic cells. And so the cells can be connected in a series to increase the voltage, like we'll learn what a car battery does. However, batteries can be placed in series to increase the voltage. They just increase the amount of electrons. In primary cells, we're talking about the difference between primary cells that are not rechargeable and secondary cells, which of course are rechargeable. First, wet cell. What does a wet mean? Well, that means it's going to be aqueous. Aqueous, right? We're in water. The Daniel cell happened to be an 1836 British chemist came up with this. And there's a picture of an actual Daniel cell that I clipped from the internet. And here's a drawing of it. And it's one of the ones we saw. It was the reduction was copper, 2 plus, going to copper, plus 2 electrons, going to copper. And that, of course, is what? 0.34 volts. And then the oxidation was zinc solid, going to zinc 2 plus 2 electrons. And that standard reduction potential is 0.76 volts. And so overall, we have copper 2 plus, aqueous, plus zinc, going to copper solid plus zinc 2, with a standard potential of 1.10 volts. In this case, you can see sulfuric acid is our electrolyte, so you have sulfate in there as your anion. And that's 1836. It's pretty good. One of the problems with the wet cell is that water, we'll say this, H2O is approximately 8 pounds per gallon. Water's heavy. And so what, like your car battery, they're heavy batteries. So for portability, we don't really want wet cells. That came up with the Lachance dry cell. Now this is in the 1860s. 1860s. Right. It's a dry cell, so it means there's not a lot of water. I'm sure there's going to be some water in them, but not much. The anode is still zinc. Zinc solid going to zinc 2 plus 2 electrons. You see, the anode is actually the zinc case. It's actually a zinc case. The cathode, 2MnO2, manganese 4 oxide, plus 2 electrons going to manganese 3 oxide, and then 2O3 solid. So overall, we have zinc plus manganese 4 going to zinc 2 and Mn2O3. So that's our overall. And the voltage is 1.50 volts because it's manganese and zinc. One of the problems that we have is this right here. And as we know, NH4 plus, ammonium, is an acid. And acids don't really, and zinc reacts with acids. So this is not the best situation for long-term stability. Bring in the alkaline battery. Right? The alkaline battery, right? You have the anode is pretty much the zinc, a little change. So the oxidation is zinc solid plus 2 hydroxides going to zinc hydroxide plus 2 electrons. So it's just not aqueous. It's a cathode is 2 manganese 4 oxides plus 2 waters plus 2 electrons going to 2 MnOOH solid plus 2 hydroxides. So our overall reaction is zinc plus manganese 4 oxide plus 2 waters, giving us zinc oxide plus MnOOH solid. And so what's nice about this? These have longer life. Why? Because zinc no longer I have a mistake up here. It's not zinc hydroxide. Just notice that. CNO plus H2O. There we go. There we go. That's a little fix there. So there's a fix. Longer life. Zinc no longer reacts with the acid. Also, it has actually higher power, something we wouldn't know. And that's because there's more efficient movement of ions, which is wonderful. So, and we still use these today, right? Duracell, Energizer, and there's a bunch of other brands, and so they're all good. All right. The mercury and silver, the button batteries. These batteries, all right, they replace manganese with mercury. Or Ag. Okay. And so for mercury, think of a nice, they're like watch batteries, right? The mercury and the silver batteries. And so when we talk about mercury, we have the anode is still zinc plus 2 hydroxides going to zinc oxide plus water plus 2 electrons. The cathode now is HgO plus 2 electrons going to Hg. Right? Our standard potential happens to be 1.3 volts. And why do we like this? They're small, which is nice, and they have a stable voltage. They work well. All right, and so that's why we use them. One of the reasons that, and I didn't talk about the silver one, one of the reasons we don't use the mercury is that the mercury is disposing it is toxic. For silver, the cathode reaction is Ag2O solid plus water plus our 2 electrons going to 2 silver plus 2 hydroxide. Technically, there's 2 hydroxide up here too. And there's a water on this side too. And then lithium cells that we have. Lithium cell, we replace zinc with lithium. So these are the non-rechargeable batteries. So you have your anode is lithium going to lithium plus an electron. And our cathode is manganese 4 oxide plus an electron going to Mn2O3. And our reduction potential is around 3 volts. So double the voltage. And these are used in a lot of applications. We have like bright lights and whatnot. So those are the primary storage batteries. Then we'll dive into secondary batteries. And first one is lead storage batteries. And we can recharge these. All right, so a lead battery is a series of 6 cells providing 2 volts each for a total of 12 volts. So the electrolyte is 30% H2SO4. The anode's lead. So our anode would be Pb solid plus HSO4 minus going to PbSO4 plus H plus 2 electrons. And that standard protection is 0.296 volts. The cathode, we have lead 4 oxide plus 3 H pluses plus HSO4 minus 2 electrons going to PbSO4 solid and 2H2O is 1.62 volts. So overall, we have lead plus lead 4 lead 2 sulfate and 2 waters. The standard reduction potential of 1.924 volts. So with this, the product, which is lead 2 sulfate, adheres to the electrodes. And the reaction can be reversed by applying an opposite potential. Eventually, after several years, the lead 2 sulfite is dislodged, and the cell can no longer be recharged. That's the lead storage battery. Next one is nickel cadmium. These were fun. The anode was cadmium plus 2 hydroxide going to CdOH2 plus 2 electrons. All right. Cathode is NiOHO plus the electron going to NiOH2. The products here adhere to the electrodes. So the process can be reversed and the cell recharged. Kind of fun. The voltage is about 1.30 volts, and the electrolyte is concentrated KOH. These are rechargeable. They have a long life. Right? However, if I can spell however right. However, recharging incorrectly can lead to battery breakdown, and cadmium is toxic. Problems with the nickel cadmium cell. So then there came the nickel metal hydride battery. Still, electrolyte is concentrated KOH still. The anode is a metal alloy with dissolved hydrogen. All right. And there's the oxidation of H0 to H+. The cathode is still the same nickel, coated with nickel 2 oxide. It's still I didn't write that down. Still, the cathode is nickel coated with NiO2. That's reduced. So we have M, some metal, plus, I guess not plus, dot, H, that's a solid, plus hydroxide, going to metal plus water, plus the electron. Then you have NiO2, plus 2 waters, plus 2 electrons, going to NiOH2 solid, 2 hydroxides. All right, so think about these, and now we're getting into batteries that are being still used. So, for example, when I was in grad school, Dow and DuPont both came and gave talks to our seminar. Right, so usually every week you had a seminar where you go to, and each of the fields did, like analytical chemistry had a seminar, physical chemistry had a seminar, inorganic chemistry had a seminar, or organic chemistry had a seminar. And somebody would come in, and either somebody internally or somebody externally would present research. And this happens all over the place. Well, Dow and DuPont would come in once a year, it seemed like, and they would talk about things they were doing, but they would never give you any chemistry. Like one was talking about bowling ball surfaces. And another one was talking about, I remember this, they were talking about LED screens because they didn't quite have LED screens for phones yet. Right? Now we do, but they didn't at the time. They were working on that. But of course, they didn't tell you anything about the chemistry. There was no chemical reactions, no compounds, nothing, right? Because they're all proprietary and they're trying to get the material patented and produced and make money, which nothing wrong with that. But we didn't hear anything about it. It's very hard to find a lot of information on some of this nickel metal hydride and their next battery that we're talking about, which is the lithium ion, because they're big right now. And if you can make a better battery, you're going to sell more of your electronic device. That's the bottom line. If you had a cell phone battery that would last 3 days with some of it with continuous use, pretty much, versus most of the cell phone batteries are 1 day with continuous use at the most, you would sell a lot of phones. So that's where we're at. We're not going to find much more out of this, and it gets kind of complicated too, beyond Chem 2. So the details are going to start to dwindle. We're going to talk about it a little bit. But with these nickel metal hydride batteries, they are rechargeable. They have long life. They're more environmentally friendly than nickel or that nickel cadmium. All right, and then also there's a greater energy density, which is important. All right, lithium ion battery. And this is again, electrolyte. Is concentrated KOH. All right. The anode is graphite with Li ions. The cathode is a transition metal and lithium. Right? It's a metal oxide. It's an oxide. So again, there's charge and discharge, right? It works on lithium ion migration from the anode to the cathode. All right. It's beyond the scope of the class. It's a very advanced stuff. I don't actually, even me personally, I don't know how they work. The rechargeable, they have long life. They're very light. They have good energy density. They can be any shape you want, which is nice. So they are the hot thing right now, lithium-ion batteries. Will something else come out? Maybe. But they are big. Next thing we're going to talk about is fuel cells. And here's a hydrogen oxygen fuel cell. There's different types of fuel cells. This is the one we'll talk about. So if you look, we have, what's going on here? I have hydrogen gas coming in, oxygen gas coming in. All right, O2 is going to hydroxide, H2 is going to H+. They make water. All right, so the net reaction, the two half reactions are there. H2, hydroxide going to water, 4 electrons. O2 and water, and 4 electrons going to hydroxide. So overall, they make 2 waters, right? 2 H pluses, 1 O2, 2 waters if you add those reactions up. And E cell is 0.40 volts. And the oxidation half cell is 0.83 volts. So the overall cell should be 1.23 volts. That's what we should get. Now, in practice, I don't think it's that much. I think we lose some due to heat, right, because of the resistance. And I think mass transfer is slow. I think it's kind of a slow, kinetically slow process. So I don't think we actually get that much out. But that's a fuel cell. And for me, this would be ideal because the only product is water, and that's a very green product. And I believe I have a picture down here. I do. Here's hydrogen in a small little Toyota. And so I always end this talk here with fuels. Like, what do we use for cars? What's the motion forward? Right? And I'm not the authority on this or an expert on this, but what are the options? And obviously, hydrogen and hydrogen fuel cells are an option. Right? You got electric, which is an option. Ethanol, which is an option. Biodiesel is also another option. Natural gas and propane have been talked about. And so, what's the best? What do we use? Well, currently we use gasoline. And why do we use gasoline? Because we're evil? No. Right? And there's always a couple questions I ask. One, we're probably going to use the most cheapest or most inexpensive way to go forward, right? Because I make a finite amount of money, and I'm not going to spend all my money on a super duper car that does zero emissions and not eat food or not have a house, right? That's not what's going to happen. So what do? Right? So hydrogen would be nice, except if you look at the storage of hydrogen, it's kind of tough. We use gasoline and diesel because their energy density is so great and the refueling is so great. If I would have a Tesla, no problem, but they're $96,000 or something like that, or $80,000 for a new Tesla. I can't do that. There's no way I can do that. Even if I was just me and I didn't have a family, I still couldn't afford a Tesla, a new one. And so what would I do? What should we do, right? And the other thing with the Tesla, I drive 200 miles. It takes me however long to recharge the battery. So it's a good question. What's the best choice? And I don't know if we have the best choice yet. Obviously, when people talk about green and emissions, they're talking primarily about CO2. But there's more than just the end user, you and I driving the car, with CO2 production, right? Like making the car matters. And disposing of the car matters. So all these things do come into play. And so what's the best choice? Again, I don't know. Obviously, using hydrogen and oxygen to make water would be the greenest choice. Can we do that? I don't know. Maybe we can in a few years. I don't think we're there yet. And so, hybrids are common right now because we use the braking and other things about the car's natural functions to produce electricity to help power it, which I think is great. But again, I don't own one because they're not cheap, and we all have different needs and different purposes for our vehicles. So again, what's the best option? I don't know. I always throw this out there, and this does hopefully whet the appetite a little bit to look into these. And when you make a choice to buy a car, you actually think about what's your need, what's the cost, right? But green of all, like electricity is not even that green, right? Depends on how you get your electricity, right? Do we get now where I live? We're a nuclear powered state, so it's actually pretty green when it comes to CO2 production. Very little. If I did biodiesel, it's great. It's renewable because they're using the oil for cooking and whatnot, but it still produces CO2. So the whole thing is going on, right? It's the whole talk, whole debate, and nobody really knows the answers yet. So don't feel bad if you drive a big SUV or something like that. You drive what you need to drive, okay? But it is something that we do as a people need to think about because, again, oil won't be around forever. So even if CO2 wasn't a problem, let's just pretend that CO2 is not a problem. Let's pretend we don't care about emissions. Well, eventually the fuel itself will go away. It won't go away soon, but it eventually will, right? We don't have an unlimited supply of fossil fuels, so we do have to be looking for alternative fuels, and there's a lot of research being going on there, and I think that's very important that we continue that research. And so that basically concludes what we needed to discuss about fuel cells, batteries, and whatnot. The next video will go into cell potential and concentration, and how cell potential can be drastically different based on the concentration. So hopefully that made sense. Hopefully that worked out for you, and we'll see you next video. Take care, guys.